Hi, I'm Mc Carthy. This is my first GNU Radio conference, and I'm really excited to be here. So I just graduated from Cal Poly. I'm now going into my master's, and my partner, Ben Duvall, my advisors, Dr. Dennis Derrickson and Steve Dunton, and I have put together this presentation to talk about our efforts to use the Raspberry Pi 5, the Lime SDR Mini 2.0, and GNU Radio in our projects and curriculum at Cal Poly in the last 2 months. So just a general outline of the things I'm going to be talking about. I'm going to talk about our high-level goal of we want to use a software-defined radio in a multi-hop mesh network. This is a goal that we still haven't achieved yet. We're working towards. I'm going to then talk about EE 504, the software-defined radio graduate laboratory course, and our efforts to incorporate GNU Radio into the curriculum of that class. And then I'm going to talk about our summer research efforts with OWL integrations to incorporate GNU Radio with the cluster deck protocol. And then I'm going to summarize everything and talk about where we're going next. So we have a partner, OWL Integrations, and they were the people who made the cluster deck protocol. It's a pretty funny name, and it came out of the Google call for code in 2018. They're a simple LoRa-based mesh network where their radios are called ducts. Your duck link is going to be like a chat or sensor node. Your mama duck is a repeater, and the papa duck is your gateway. Like I said, everything is based off of LoRa right now, but the idea is that we want to, OWL Integrations would like to have a higher data rate link to increase the capabilities of their mesh networks. So OWL Integrations has been a partner with Cal Poly for a few years now. They've sponsored multiple projects. As I said, it's a multi-hop mesh network protocol. It's pretty simple. As of right now, all of their software is open source, so you can go to their GitHub and download it, and if you have the correct software, or excuse me, the correct hardware, you can make your own duck, or they have their own ducks themselves that come in a case. And they've sponsored this research with GNU Radio. Uh-oh. Oh, I got the wrong one, sorry. So yeah, this is their duck Rev 1. Inside the case, it's a T-beam and SX1276. And it's becoming a little bit outdated now. So simultaneously with this research that we've been doing with GNU Radio, they've also sponsored 2 projects at Cal Poly working on revising the boards for increased capability and encryption. But recently they've also come up with this idea of this Quad Pro, where instead of a dedicated microcontroller and in the embedded environment, they would like to move the cluster deck protocol to a more operating system-based environment on the Raspberry Pi computer. And so software-defined radio is not necessarily intrinsic to this, but it does open up the opportunity for software-defined radio. So this is where our research has been with GNU Radio, is on the Quad Pro. So there's a list of hardware that we used for EE 504, the lab. We just used the Pi 5 and the Lime Mini. But then on top of that, for the summer research with the Quad Pro, we had a few sensors like the GPS and the camera. And then we also had a dedicated LoRa transceiver because, like I said, we wanted to get a Raspberry Pi-based duck working, not necessarily an SDR duck working. And then just on the right, we have our extra equipment. So we developed on the we developed mostly on the Raspberry Pi, and we had extra ducks to test with, and we had some test equipment. We also used some software. Obviously, we used GNU Radio. That's why I'm here. And we ended up using Dragon OS as well, which I will talk about in a little bit. Mr. Taparel gave a great speech on his LoRa SDR out of tree module, which I would not have been able to do anything in this project without, so many thanks to him. And then we also used the Lime Suite drivers. So it could have certainly been user error, but given how new I was to software-defined radio, I had a lot of trouble getting the drivers to work correctly for the Lime Mini 2.0. And when I reached out on the forums, it seemed like their software might be in a kind of interesting place where the Lime Mini 2.0 was not necessarily, I was having trouble getting the drivers working on their old version of Lime Suite, but they're currently in the process of making the Lime Suite NG, which is their updated version of the drivers. And unfortunately, neither of them worked, but that's where Dragon OS came in. I was able to use Dragon OS to pass the self-tests with the Lime SDR, and that is the only way that I was able to use the Lime SDR, but it worked. And in terms of EE504, it actually provided a lot of benefits. So besides the driver problems, the Lime SDR also struggled. It has its own out-of-tree module, but it is not supported in the current version of GNU Radio. Thankfully, SOAPy SDR does support the Lime SDR in the current version, so we were able to use it with GNU Radio 3.10. And what else? So I would say that it wasn't necessarily beginner-friendly. I had almost no experience with software-defined radios and literally no experience with GNU Radio before the start of this year. So it took me a little bit of time to figure out what I was doing with this. But at the same time, I think that there's a lot of room for me to grow with the Lime SDR. It has an onboard FPGA. It has 2-channel TX-RX. So there's a lot of capabilities with it. And then it also fits in line with Project Owl's mission statements and goals of low cost, or relatively low cost, I should say, portability, and open source. The Lime SDR also checks all of these boxes. And then, yeah, I think that there were a lot of things that I found really cool about the Lime SDR. Like, for the price, it had 2 channels. It has a good amount of frequency range. And the most frustrating thing was the drivers. After that, I had a lot of fun using it. So just a little bit more about me before I go into EE504. Like I said, Project Owl has sponsored a lot of different projects through Cal Poly, senior projects, through Cal Poly, and the one that I worked on last year was exploring software-defined radios and how to use them in mesh networks. It was kind of like a pathfinding project where nobody really at Cal Poly or in Owl Integrations knew much about software-defined radio. They didn't really know anything about GNU Radio, so I was tasked with using the Lime SDR to kind of pathfind this. And I had some successes. So I taught myself, I needed to teach myself GNU Radio as quickly as possible. So obviously I went to the wiki because that is the best place to teach yourself. And then also I volunteered to TA for EE504. One of my professors was the professor for this class, and it had never used GNU Radio in its curriculum before, but given that I had spent the last 2 months using teaching myself GNU Radio and using it, I volunteered to edit some of the lab curriculum at the latter half of the lab to use GNU Radio instead. So as I said, the software-defined radio lab, typically it was just done with the analog devices Pluto and MATLAB, all of the labs. But given our work with GNU Radio in the last few months, we wanted to implement GNU Radio in the second half. So we only had 5 weeks on the quarter system to get students onboarded with GNU Radio and get them, the end goal being they make their own flow graph that does something slightly unique. And to do this, we, again, used Dragon OS. Dragon OS saved us a lot of time, not just for driver issues, but also just downloading everything. So all of your dependencies, all of your drivers are already downloaded on Dragon OS. All you have to do is maybe update and build your out-of-tree modules. So I gave a tutorial for that, and then students were tasked with very basic simulation flow graphs, kind of more or less based off of the wiki. And they were just simple flow graphs to teach students about, how you can tackle a problem in GNU Radio, how flow graphs work, things like that. And then once, as we moved forward, students had a little bit of experience with GNU Radio and hardware working, so we wanted to move to hardware flow graphs as quickly as possible so that we could do something interesting. I found myself having the most fun when I was actually using something over the air instead of trying to simulate everything. So the FM receive was a good one in kind of the second week, where it's 3 or 4 blocks, and all you have, you just have to set up your hardware correctly, and then you can listen to the radio, which students found pretty interesting. And I found it, relatively engaging for not having a ton of experience with GNU Radio. And so through that, we worked on writing some simple blocks for ourselves, worked with stream tagging and stuff like that, and with the eventual goal of, this is week 4, coming up on the 5th week of GNU Radio, and students had to submit a project. So the instruction became more specific to what students were interested in, and less about you do this and then you do this. So one of the most interesting final projects for this class was students made a very crude, I wouldn't even call it a Doppler radar, but they saw the Doppler effect by sending out a pulse, and then they were moving a piece of aluminum foil backward and forth, and they were able to roughly see the velocity of that piece of aluminum foil. So the summer, or with EE504 done, we finally had more than just one person who knew how to use GNU Radio at Cal Poly. So Owl Integrations sponsored a summer research effort into developing this Quad Pro, which was not necessarily using software-defined radio, but there was kind of 2 sides to it, where Benjamin Duvall, my partner, and I, we were working on developing with GNU Radio, and the rest of the team was working on porting over the cluster deck protocol onto an operating system. So this was done by all undergraduates, so there are probably many inefficiencies or things that we could have done better, but at the same time, I'm very proud of the team for what they did in 10 weeks. We made 3 separate processes that loosely follow that CDP stack that I had a picture of up a while ago, where our web interface program is hosting the Wi-Fi hotspot and running the web server so that people can send messages on the radio. We have our CDP handler that does all of our multi-hop mesh network logic, so not just packet encode and decode, but like retransmission if needed, other things like that. And then our SX1262 is not a physical layer. It is actually just an SPI driver talking to the SX1262. But it also gets me into my next point of we used Redis streams so that these 3 processes could be separate and interchangeable, which we will get to later. But Redis streams was used because it was simple, easy, and we could make queues that were asynchronous, so all of these processes could do their work independently of each other. So yeah, at the end of the 10 weeks, our main team for the Quad Pro was able to get this software working functionally, but there's still a lot of bugs that we have yet to figure out. And then the team working on GNU Radio, we tried to develop our skills a little bit more with GNU Radio and tried to compare our flow graphs to the SX1262 to see if we could end up replacing this 1262 with this Lime SDR. And so the 1262 has an FSK chip, or excuse me, an FSK modem built into it as well. I actually just learned that FSK is a part of LoRa, technically, but it also is able to do FSK completely by itself. So this kind of gave us the idea of what if we built an FSK flow graph, because that is relatively easy, but would also give us a lot of experience writing our own modulator and demodulator, as well as eventually we wanted to write a packetizing system for this FSK transceiver. So that's what we did. We wanted to compare, can this Lime SDR replace the FSK, or excuse me, replace the SX1262? And we kind of expected that the Lime SDR is going to have worse performance, but it is going to be a lot more flexible, and we're going to have the option to change our flow graph depending on the situation, versus the SX1262. We can only interact with it through SPI. And just a little bit more about our testing. We compared mostly bit error rate, but we also looked at SNR and RSSI. We compared to the old duck, so this one, the 1262 or 76, but it was not able to do FSK mode due to an outdated driver for the T-beam. But the two ones that we really wanted to compare were the 1262 and the Lime SDR. And they're just two different systems at the end of the day. The power output is going to be completely different, and we interact with the 1262 over SPI versus we send data directly over USB to the Lime SDR. So it's just not a one-to-one comparison, so this isn't going to be rigorous testing necessarily. It's just to get a finger on the pulse, for lack of a better way to say it. So as I said, Mr. Taparel was instrumental in my success with LoRa. I had known about GNU Radio for maybe 2 months at the point of trying to implement LoRa, and there was no possible way that I was going to reverse the LoRa PHY in 2 months. So Mr. Taparel was extremely helpful, and throughout the end of last year, or the end of the last school year in the summer, I've worked on some custom blocks for automating testing and eventual integration into inter-process communication. As for the FSK modulator and demodulator, Ben took a big lead on this, but it's the FSK modulator and demodulator are pretty simple. You break everything down into bits, and then you have a frequency for 1 and a frequency for 0, essentially. And demodulating is doing the reverse. But we didn't want to just make a demodulator and modulator. We wanted to make a packetizing system of some sort. So Ben wrote a block for making a CRC and then checking the CRC, and then also added logic to request a retransmission if there was a CRC fail. And this was instrumental in making our FSK flow graph reliable at all. Sure, our data rate suffered because we had to retransmit multiple times, but we were getting correct packets through most of the time. So this is just our testing setup. You guys might look at this and see the problems that we had because we were very inexperienced with software-defined radio, and so testing from a meter away with LoRa, with the LoRa SDR flow graphs, that's going to give us a significantly higher signal-to-noise ratio than we need or want to demodulate LoRa. So this honestly was probably the biggest source of our bit errors, and we're going to have to redo all of this testing. But that's okay. This is a learning experience, and that's why I'm here. And other than that, we tried to keep it relatively similar, but it wasn't a robustness test as much of it as just a usability test. The FSK testing looked at the exact same. We just didn't have the 1276, and we tested across bit rate and frequency deviation. And this is just a picture of our SDR test setup. In this picture, we were using an SMA, but when we ran the majority of the tests, it was over the air. But yes, the SNR was still significantly higher than we wanted when we were running the tests. So yeah, most of this data is moot given that we've learned what we did wrong here. But just general notes is that we were surprised by how easy it was to use, especially the LoRa flow graphs. Taparel's work was amazing, and it was really intuitive to people who have never really experienced that much with GNU Radio, especially an out-of-true module like that. And the 1262 had some odd problems. We had a higher bit error rate than we expected for a dedicated transceiver, but again, we were undergraduates not doing the most rigorous testing in the world. As for FSK, Ben's addition of the CRC check was instrumental in making reliable packet reception possible. We were getting a lot of errors with the first or second packet, but if we keep checking the CRC and retransmitting, we were able to get reliable packets through without bit errors, which was really cool. And oddly, with the 1262, we were having low data rate, huge problems with low data rate. We were having huge packet errors. So just to summarize, the 76 is older. We couldn't use FSK on it, and it's being phased out as is with OWL. The 1262 was all right, but we had to interact with it over SPI, so it wasn't ideal. And it wasn't as good as we thought it was going to be. And the Lime Mini, our conclusions about it are probably not valid, given that we know how many things we need to change about our testing setup before we can make solid conclusions about it. But at the same time, it was really easy to develop our FSK flow graph, especially. We were able to add functionality and add a lot more, and there's a lot more functionality that we can add in terms of inter-process communication, automated testing, things like that, that were really fun to learn through GNU Radio. Going forward, like I said, we want to eventually use the software-defined radio instead of the SX1262. So we want to replace this 1262 SPI driver with a SDR driver of some sort that can eventually select parameters and flow graphs and then send a packet out on that without the other two processes needing to know anything about it. So it just sends a cluster duck protocol packet to the SDR process, and then that cluster duck protocol packet gets sent out, and it doesn't have to worry anything about LoRa or anything like that. But we're not there yet, especially because we have so much to learn about software-defined radio and GNU Radio, and hence the reason that I am here. The GNU Radio experience at Cal Poly is very, very early on. I had nobody in Project OWL or Cal Poly really knew much about GNU Radio besides the name. So this has been a pathfinding project of how do we use GNU Radio, and I'm really glad that I'm here to learn so much and hopefully get suggestions from you guys of what we can do to implement this or improve our flow graphs. So I will be around. Please talk to me if you have any suggestions. But with that, do you guys have any questions?
Did you use the tutorials for GNU Radio, and were they helpful, and how did you experience that?
Yeah, I should have spoke more on that. I personally used all of the tutorials, and they were super helpful for me without anybody to go to of like, oh, what does this mean, or stuff like that. The tutorials were very helpful. And yeah, there's just the open source community, especially with GNU Radio, was extremely helpful. Everybody wants to help you if you ask a question. So I never was like scared of like seeming dumb or something like that if I had a question. But at the same time, it took me a little bit longer, and it was kind of a tedious process. And I didn't imagine. So the EE504 lab is once a week, 3 hours a week. So there wasn't time for students to read through the tutorials and go through all of those in that amount of time, and then also be able to produce something themselves, probably. So the point of my tutorials that I produced was just to kind of condense some parts of the wiki tutorials and also add parts where it was like, not the entire answer was given. So instead of walking them through how to do everything, there's a part that's left missing that students have to fill out so that they can learn more. But to answer your question, yes, they were very helpful.